All right. So I'm going to explain Shor's algorithm. And to do that, I'm going to explain how it cracks RSA keys and why this is an issue to the internet. So, what are RSA keys first? First off, RSA encryption is a combination of two prime numbers multiplied together to make a bigger number. Now, this is very secure when these two numbers are really big and they're multiplied together to make an even bigger number because it's not hard to multiply them, but it is hard to factor them back into their original factors. The reason that this is a issue is that with quantum and Shor's algorithm, cracking and recreating RSA keys becomes way easier and actually possible, which can threaten internet security and our data security. How does Shor's algorithm actually do this, though? Well, Shor's algorithm can do this because the quantum computers can factor using period math on these scales. Now, here's an example of period math, or period finding is the other name for it. So, an example here is we have 15. Let's say we did 3 times 5 to get 15. That's 2 primes to get our number. Um, Here you can see that for each x, which is 0 through 8, we can get the remainders. And if you look at the remainder list, you'll see a pattern starts to emerge. It is this pattern that is known as the period, and this period is what's going to allow Shor's algorithm to solve the to solve the problem. Now, Shor's algorithm uses quantum computing to find these periods, and once they're found, it can use regular classical math to find the factors. The important steps is something called quantum Fourier transformation, or QFT. This is related to discrete Fourier transformation, but in this case, it's actually for quantum computers and not regular classical computers. So, in Shor's algorithm, the quantum computer creates a superposition of many possible values, and QFT helps reveal the repeating patterns after they are measured, which is allowed to, or which helps us calculate the period. Now let's do an example. So in our example, we have n equals 15. Let's say our guess equals 2. We're then going to find the period using the QFT, and here is the example. So our remainders are 2 for 1, or 1 for 2, 1 is 2, 2 is 4, 3 is 8, and then at 4 we have 1. And this is the end of the pattern because when 2 is 0, the remainder is always going, or when x is 0, the remainder will always be 1. So we'll know we're at the end of the pattern when we find 1. So at this point, we know that the period is 4. Next, we then calculate with our guess the known to the exponent of the period divided by 2, which in this case will give us 4. And then we use our Euclidean algorithm, which will then be 4 minus 1 modulus 15. And we'll be able to, you will be able to see that this is a factor or not based on 15 modulus the number that comes back, or you'll be able to check for that, and that's how the computer will know. So in this case, 15 modulus 3 is 0. So that's one of our factors. And luckily enough, in this case, the other factor is also found in our Euclidean algorithm, which is 5. That's not always the case, and I do want to note that that this is a coincidence, and you would actually take your found factor and you would divide the main group by the found factor to find the other factor. Now, um, now that's the basic idea behind Shor's algorithm, and the reason that this matters is because it can break a lot of internet security as well as the HTTPS, the banking, digital signatures, and it would allow you to remake them and leak information. This is just a problem overall, but we don't have to worry about it too much because quantum computers aren't at the state where they would be capable of doing this due to error and size constraints. And that's Shor's algorithm. Where is my stop recording button? Thank you.